The last topic of this lecture will be an integration technique called partial integration. Partial integration is in fact nothing but a sort of anti-product rule of differentiation. Let us recall the product rule. So, suppose that we want to compute the derivative of the product of two functions f and g, then we know by the product rule that this is equal to the derivative of f multiplied by g plus f times the derivative of g. An alternative way of expressing this is saying that f prime g, the derivative of f times g is equal to f prime g plus f times g prime. Now we can rewrite this by taking this term to the left hand side. So we have that f prime g is equal to the derivative of f times g minus f times g prime. Clearly we can take integrals on both sides, so this means that the primitive of f prime g is equal to the primitive of the first term on the right hand side minus the primitive of the second term. Clearly, now if we look at it a little bit, then it's clear that if we take a derivative and then a primitive, we end up by doing nothing at all. So the first term is equal to the product of f and g, and the second term remains the same. Now, why would one want to do this? Apparently, this integral, the first integral, is very difficult to calculate, and we hope that the second integral here is easier to calculate. Let us illustrate this by an example. The example is the following. We are required to compute the primitive of x times e to the power x. Now, at first sight you won't have any idea how to do this at all, but an idea is to try to apply partial integration. And to do so, we have to write this as a product of two functions, f prime and g. Now, it's not clear. It's not the choice of f prime and g is not unique. Of course, you have to look a little bit, but let us try to call f prime the function e to the power x and g the function x. Okay. If f prime x is equal to e to the power x, then f is the primitive, must be equal to e to the power x. Of course, we can add an arbitrary constant, but in partial integration we will not do this at this stage. Of course, if g of x is equal to x, then it's easy to compute the derivative, which is equal to 1. So what do we get by applying the partial integration rule? So let me emphasize that the partial integration rule is just this underlined red, this part underlined by red. Then what we get is, on the right hand side, is the product of the two functions f and g, which is equal to x times e to the power x. And we have to subtract the primitive of f, which is e to the power x, multiplied by g prime, which is equal to 1. But now we get an integral here, which is quite easy to calculate, because the primitive of e to the power x is simply e to the power x. And of course, we have to add an arbitrary constant. So this difficult integral was in fact quite easy to solve. Now, I already said that it is not always clear which function should be f prime and which one g. So suppose that we would have made another choice. We would have swapped our choices and put f prime x equal to x, which makes f of x equal to the primitive of x, which is half of x squared, and g of x equal to e to the power x. Then, of course, g prime of x would be e to the power x itself. What would we have got in this case if we would plug in these functions into our formula? That the desired primitive is equal to the product of the functions f and g, so which makes it into 1/2 of x squared e to the power x minus the primitive of the primitive of f, which is 1/2 of x times x squared multiplied by g prime is e to the power x. Now clearly this relation is true, that is no doubt about that, but this integral over here is really much more complicated, and we wouldn't know how to solve this one neither. So everything depends on the choice, and of course what I should point out is that it is not always clear that this trick will help at all, but one can always try. So now another example is the following. Suppose that we want to know the primitive of the natural logarithm of x, or the logarithm with base 10 of x or whatever. Again, we wouldn't know how to do it, and clearly if you look at it, it is not a direct example. It doesn't seem to be a very clear example of partial integration. However, we do not have that many methods, and we have to try something. Now, how could we make this natural logarithm of x into a product of two functions? Well, it's always a product of the function that is equal to 1 everywhere in the function itself. Okay, so we can try it, and what could one do? Well, again, the best way seems to be to put the natural logarithm into our function g and the f prime into the function that is everywhere equal to 1. Now, why would this be so? Well, we couldn't put f prime equal to the natural logarithm of x, because then it wouldn't help us any further. We would still have to compute the primitive of ln x. So this is the effect, in this case, the unique choice. So what do we get? F prime of x is equal to 1. So f of x is equal to x, and g of x is equal to the natural logarithm of x, which means that g prime, the derivative, is equal to 1 over x. Okay, we'll plug this into our formula, and what we get then is that we have to compute the product of f and g, which is x times ln x, and we have to subtract the primitive of where is it? F times g prime, so this is x multiplied by g prime is 1 over x dx. Aha, but now we end up with a very nice simple integral, because x multiplied by 1 over x is equal to 1, and we know the primitive of that one, which is equal to x. So we end up with x multiplied by the natural logarithm of x minus x plus an arbitrary constant c. So this gives you our desired primitive. Of course, what you always should do, if you're not completely sure about your work, is to check by differentiation. And this is in fact a sort of global warning. The last example of partial integration is an example where you get a phenomenon of cycling, which will be in the next video.